Hello, everyone. Welcome to Lab 3, and this is for both Physics 206 and 207. In this lab, we're going to look at two particular motions, one where a ball is being dropped and one where an individual is performing a vertical jump, like a maximum vertical jump. And we're going to digitize the movies of those motions, create graphs, right? The position versus time, the velocity versus time, and the acceleration versus time in the vertical direction. And then we'll analyze those graphs. Okay, so we'll analyze the motions by examining the graphs. And then the second part of this experiment, we'll look at projectile motion, right, which is like two-dimensional motion. And I have collected some data, so you guys can look at the video where I show you how I collected the data. You're going to analyze the data that was collected. Basically, we're going to look at the range, examine the range as a function of the angle that the ball, the little marble, is being launched at. And then also, I'm going to have you collect data using a simulation of projectile motion, and then we'll analyze that. Okay, so really, this whole lab is really like analyzing motions. So to start, what I want to do is show you guys how to digitize the movies. And what I'm going to do is I'm going to digitize a movie where someone is throwing up a ball. So the ball rises to a peak and then falls back down. And then we'll analyze the motion of that particular ball being thrown. And that will give you a really good idea of how to answer the questions when you analyze your two motions, the ball being dropped and then an individual performing a vertical jump. Okay, so let's start with that. Okay, so to analyze the movies, what you want to do is go into Pascal Capstone and then just double click on video analysis, go to open movie file, and then choose the movie that you want to analyze. Now, the ball drop and the vertical jump will be posted on Brightspace. You can download those MP4s onto your computer, and then you can analyze them. You might have to unzip them. It depends. I think if you have a Mac or an Apple, it'll do it for you. I think if you have a PC, you have to extract them or unzip them. Okay, but you can figure that out. Okay, so in this case, I want to look at this movie right here where ball's being thrown. So I'm going to double click on it. And if we can play it, you can see a ball like rising and then falling. Let me just do it more slowly. So here, right, the ball is leaving the hand, it's rising to a peak, and it falls down to the ground. So we want to analyze that motion. So to analyze it, I have to do what's called digitize the movie. And what that means is I need to locate the position of the ball in every frame. Basically, a camera was recording at 30 frames per second, and I need to locate the position of the ball in every frame as the ball is undergoing its motion, okay? But first, we need to let the computer know what a known distance is so that it can convert from units of pixels, right? Because the movie will be measured in pixels to real world units of meters, because ultimately we want everything to be in meters, right? So to do that, there's a meter stick that's in the field of view here. And actually, when you guys analyze the ball drop and the vertical jump, I put a meter stick in the field of view as well. And to tell the computer that that represents 1 meter, you click on this calibration tool here. So click on like the top part and then drag it to the top part of the meter stick. We'll say right there. And then the bottom part and drag it to the bottom part of the meter stick. And then you input the length, but it's already, the default is 1 meter, so you can just leave it at 1 meter, and that's done. So now you've told the computer that that represents 1 meter, right? So however many pixels that is between it, it'll do the proper conversion. Okay, now to analyze the movie, what you need to do is, first of all, we want to magnify this because it's hard to see. So if you click on this magnifying glass icon up here, and then we can bring it to where the ball is, right? Just left his hand, click on it and click on it once more, and it should advance the movie 1 frame. And you're just gonna follow that as best you can for each of the frames. It gets tricky near the top. It's kind of hard to see near the top. And I want to go until right before it hits the ground. So I'm just looking at the motion when the ball's in the air. So actually that's good. Something like that is fine. Okay, so now what I want to do is I need to create 3 graphs. I want the vertical position versus time, the vertical velocity versus time, and the vertical acceleration versus time. So to do that, over here, I'm going to move my image out of the way. I need to click on graph. And then all you have to do, you don't even need to bother with the X. It'll automatically put in time correctly for the X. You go to the Y axis, and we're going to choose object 1, and then I want Y, which means the Y position. And then I'm going to zoom in. Okay, so that looks reasonable. For the title here, I'll say vertical position versus time. Now notice that it connects the data points with line segments. We want to get rid of those. So the usual, right? I highlight a data point, right click, uncheck show connecting lines. And then we want to do a fit. What do you think would be a good fit? Well, for this data, it's probably going to be a quadratic fit, right? And it should be, in theory, it really should be quadratic. So I'm going to do a quadratic fit. Okay, so that's vertical position versus time. Now I'm going to click on graph again. And now I want to plot the vertical velocity versus time. So again, I just go to the y-axis, object 1, and now I choose Vy, right? Make sure you choose the y, not the x, because this is be the horizontal velocity. We don't want to look at that. We want to look at the vertical velocity. Again, I will scale it by clicking on this left icon. Now, let me give it a title. So I'll say vertical velocity versus time. I will get rid of the line connections. In this case, it looks pretty much linear, right? So I'm going to do a linear fit here. So we'll do linear, okay? And then one more graph, so we'll click on graph again. And now I want the vertical acceleration versus time. So I'm going to choose AY. And then zoom in. Actually, it looks kind of messy. We're going to fix that in a second. Let me give it a title. So I'll call it vertical acceleration versus time. Now, in reality, this should be pretty much constant. We'll talk about that in a little bit. It kind of varies somewhat because there's some noise, like there's some noise in the original position versus time data, which means there's going to be a little more noise in the velocity versus time data, which means there's going to be even more noise in the acceleration versus time data. You could smooth it. There is a way of smoothing it, but we're just going to leave that. But instead, what we're going to do here is we're going to change the scale on the y-axis. So if you click anywhere on the y-axis, see where you see that double arrow there? So right click, go to axis properties, axis scaling, and let's change the maximum value to be like maybe 20, and the minimum value to be like maybe negative 30 or something, negative 30, let's say. Okay, so actually that looks a lot better. So I'm going to get rid of the line segment connections, I normally would. And then again, this should be like an average, it should be like a horizontal line that goes through all these data points. So to get that line, you have to click the sigma. There is no fit for doing an average fit, so you just have to click the sigma here. And it'll give you the mean, right? It does align an average fit and it gives you the mean there, so 9.76. Okay, now what you would do is you would copy and paste these three graphs into your lab document, right? Your lab report document. So then you can analyze them, right? You can answer the questions. So what I'm gonna do is I'm gonna pause this in a second. I'm going to copy and paste. Remember how to copy and paste? If you click on a graph, go over to the border, right click, and then copy display, right? And then you can paste it into whatever program you want. So I'm gonna copy and paste these in so then I can talk about them. We can analyze them together, and I'll do that on my iPad, right? So I'll be back in a second. Okay, so let's look at each of these graphs. So the first graph was the vertical position of the ball versus time, right? So as the ball left the individual's hand, so at 0 seconds, so let me point on the graph here, that's right here at 0 seconds, the ball was about maybe 0.9 meters above the ground, or wherever the reference point was. I don't think the 0 was exactly at the ground, but around the individual's feet. Okay, so it was a little bit above the ground. And then as time goes on, so on the x-axis we have time, as time goes on, what happens? Well, the ball is going to rise. So remember this, the y is the vertical direction. So the ball is increasing in height. It reaches a peak somewhere here around 0.3 seconds, maybe a little bit after 0.3 seconds. And then it starts going back down again until right before it hits the ground. Okay, so it rises and then falls. Now, one question I could ask you, and I do ask similar questions when we eventually talk about dropping a ball and looking at the vertical jump, and again, the motions are going to be very similar, is the rate of change of the position versus time constant or not? So remember what rate of change is, right? Rate of change is the slope of the position versus time graph. So if we look here at the slope, at the beginning, right, the slope is going to be some particular value. And how do I find it? Well, it's going to be like the slope of this tangent line, right? But it's some positive value. What does that slope represent? Remember, the slope of the position versus time graph represents the instantaneous velocity. So it's the velocity in the vertical direction, and it's some positive value. And we'll see that in a second when we look at the velocity graph. But for now, let's just analyze the position graph. So the slope is positive. Then as time goes on, what's happening? Well, the slope is still positive, but it's decreasing, right? It's becoming less steep. So that means the velocity in the vertical direction is decreasing. At the peak, what is the slope? Well, it's exactly 0, right? So for an instant, the ball has no velocity when it's at its highest point, right? It has no velocity. And then after the peak, the slope is negative. At first, it's small negative, right? Then it's more negative, and so on. So what does that mean? That means the velocity after the peak is now negative, and it's becoming more and more and more negative. So it's going in the downward direction, and it's getting faster and faster and faster, right? You have a larger negative velocity. Okay, so let's look at the velocity versus time graph, because now we know that the slope of the position versus time graph should match what the velocity versus time graph is showing us. So if you look at velocity versus time graph, remember initially right? The slope was a large positive value. Well, if you look here, initially the slope is around, sorry, the velocity is around 3 meters per second. And so that slope right there is around 3 meters per second. So that represents the velocity. And then as time goes on, remember these slopes are decreasing. Well, those slopes represent the velocity, and we can see that here on the velocity graph, the velocity is decreasing, right? The vertical velocity is decreasing. And then at the peak here, remember the slope was pretty much 0, right? Because for an instant, it has no velocity right when it's at its highest point. Well, that corresponds to this point right here, a little bit after 0.3 seconds, where the velocity is 0. And then after the peak, those slopes were negative, right, on the position versus time graph. Well, that means the velocity, if I look at the velocity versus time graph, the velocity becomes negative, and it becomes more negative, more negative, more negative, more negative, more negative. So this velocity versus time graph represents the slopes of the previous position versus time graph. Okay? And then if you look at the rate of change of velocity versus time. So remember when we said the rate of change of position versus time, it is not constant, right? Because those slopes are changing. So the rate of change of position is not constant, right? That rate of change represents velocity, and velocity is definitely changing over time. First it's positive, it becomes less positive, 0 at the peak, then it becomes negative, more negative, more negative, and so on, right? And we see that reflected in the velocity versus time graph. Now let's look at the rate of change of velocity versus time, which is the slope of this graph, the slope of the velocity versus time graph. Well, pretty much, even though there's a little bit of noise here, pretty much it's constant, that slope, right? And it looks like it's a constant negative value. Well, what does that slope represent? Remember, the slope of velocity versus time is the acceleration. So what we're saying here is that pretty much the acceleration is constant and it's negative. So let's look at our acceleration versus time graph. And we see that, again, even though there's noise, right? There's some noise here. We could smooth that out a little bit. Pretty much, it's at a constant value of around negative 9.76. So it's pretty much a constant negative value, that acceleration. And again, that should match up with the slope of our velocity versus time graph. In fact, we can read off the slope here. It's around negative 9.6, right? So that's pretty close. Now, in theory, what should those values be? Well, if you ignore air resistance, if you assume there's no air resistance, right, and you throw some object up in the air, then the acceleration should be the acceleration due to gravity, which is around negative 9.8 meters per second squared. So actually, just based on our, digitizing these movies, where of course there's going to be some error in the digitizing, we're getting pretty close values to that, right? We're getting around negative 9.76, which is really close to negative 9.8, which is like the theoretical acceleration. So does that make sense? So again, position versus time. Position is changing, right? It's increasing and then decreasing. The rate of change of position versus time is also not constant, because that rate of change is a slope. It starts off positive, becomes less positive, 0, then a little negative, more negative, more negative, and so on. And what do those slopes represent? They represent the velocity. If I look at the velocity starts off positive and it's decreasing. When the ball is at the peak, the velocity is 0, so right there. And then after the peak, the velocity becomes negative, then more negative, more negative, more negative, and so on. So again, this graph reflects the slope of the previous position versus time graph. Another way to talk about velocity is you could say, on the way up, right, the direction of the velocity is positive, right? These are all positive values. But the speed, which is the magnitude of the velocity, is decreasing, right? Because it's becoming slower and slower and slower. So on the way up, the direction of the velocity is positive, but the speed is decreasing. At the peak, the velocity is 0, right? Which means the speed is also 0. And then on the way down, the direction of the velocity, which is the vector, is negative. And since it's getting faster and faster and faster, we say the speed, which is just the magnitude, is increasing. So again, on the way up, direction of the velocity is positive, but the speed is decreasing. On the way down, direction of the velocity is negative and the speed is increasing. Okay, and that's also what this graph tells us. And then finally, the slope of the velocity versus time graph represents the acceleration. In this case, it's pretty much constant. And that's what we're seeing. We're seeing pretty much a constant negative value of around negative 9.76, if we read the mean here. And we know theoretically that it should be negative 9.8 meters per second squared, which is the acceleration due to gravity, right? Any object that's, if you ignore air resistance and it's in the vicinity of the Earth's surface, it's going to have the same acceleration, whether it's rising or falling, as long as there's no other forces acting on it. All right, great. Hopefully that will help you answer the questions in the lab handout, because your motions are, again, very similar. You're going to see that your graphs are very similar to these. Okay, so again, the first motion that you're going to digitize and then analyze the graphs of is a ball drop from rest. Okay, so, and I actually kind of did this for you, although you're going to do it yourself, and you might get slightly different graphs, but they should look pretty similar to these right here. So this would be the position versus time graph, looks something like that. The velocity versus time, which should look linear, right? So you want to do a quadratic fit for your position versus time, linear for your velocity versus time. And then just like I did with the ball thrown, with the ball drop, you're also going to just do a mean, right? You're going to scale this axis so you can see it better. And you're just going to do an average, a mean. You're going to hit that sigma button for the acceleration versus time. And then you're going to answer these questions based on those graphs. So question 1 is, since the ball is dropped, we know that the y position of the ball is decreasing over time. We can also see this in the y position versus time graph, right? However, the y position of the ball, is the y position of the ball decreasing at a constant rate? Remember, the rate is the slope, right? So think about that. Question 2, how does the y velocity versus time graph justify your answer to question 1? Well, again, remember the slope of the position versus time graph is the velocity, right? So do they match up? Does the velocity versus time graph reflect the slope of the position versus time graph when you look at your particular graphs? Question 3, how is the speed, which is just the magnitude of velocity of the ball, changing as time progresses? Is it increasing or decreasing? Right? Is it getting faster or slower as it falls? Because we're just talking about speed. We don't care about direction. We know the velocity is negative. Question 4, what does the slope of the y velocity versus time graph represent? So if you understood my discussion of the ball that's thrown up, it's going to be exactly the same answer. Does your y acceleration versus time graph verify the answer? And then question 5, theoretically, what should the average y acceleration be? We've already talked about that. And then what was your value? So you can just record your value. When you hit that sigma button, you get the average, the mean, just record your particular value of the acceleration. Okay, and then the second part is going to be analyzing a vertical jump. And I wish I had more movies of this. Actually, the only one I could find is myself jumping, so you guys will have to analyze me jumping. I'll show you this in a second. I'll go back over to Pascal Capstone to show you these two movies so you kind of know what you're looking for. But again, you can download both of these from Brightspace. So you're going to create 3 graphs again, just like you did with the ball drop, right? A y position versus time, a y velocity versus time, a y acceleration versus time graph. And then there's a few questions about the vertical jump. So is the rate of change of the position versus time graph constant? So you have to just look, is the slope changing or is it constant, right? Is it linear or is the slope changing? Question 7, As a student is rising to the peak height, what direction is the y velocity? Is it positive or negative? As a student is falling from the peak height, what direction is the velocity? Positive or negative? What is the velocity at the peak height? These answers are very similar to what I talked about with the ball thrown up, because when you're jumping and we're only analyzing the motion when the individual is in the air after they leave the ground and right before they hit the ground again, it's very similar to throwing a ball up in the air, right? So if you understood my discussion earlier, then it'll be the same answers for question 7. And in question 8 is similar, right? But now we're talking about speed. As a student is rising to the peak height, is the y speed, which is just the magnitude of velocity, is it increasing or decreasing? And as a student is falling from the peak height, is the y speed increasing or decreasing? Then question 9, theoretically, what should the y acceleration be while the student is in the air throughout the jump? And then what was your actual value, right? When you did that sigma, the average fit, what did you get for an actual value? And then question 10, and you have to think about this, right? What was the y acceleration at the peak of the jump when the person reaches the highest point? The y velocity is 0, but what was the y acceleration? Okay, so just to show you how you should analyze these, let me go back to Pasco Capstone and load these videos just to show you kind of what you want to look for. Okay, so we're at Pasco Capstone again. So again, you're just going to go to video analysis, double click on it, open movie, find where you saved the ball drop, double click on it. And first thing you want to do is you want to define what a meter is, right? Here's the meter stick right here. So remember, you click on the top of the calibration tool, go to the top of the meter stick, and then click on the bottom and in the bottom of the meter stick. So that defines 1 meter. So it'll convert pixels to meters correctly. Now we want to digitize the position of the ball when it's falling, but just when the ball is in the air. So after it leaves the individual's hand, right before it hits the ground. So what you need to do is kind of like fast forward, just use like the next frame until it actually leaves her hand. Okay, so I went too far. Let me back up a little bit. I'd say right there is good, okay? Maybe you can go one more, up one more, right there. So we go to the magnifying glass, click on it, and it'll advance. Sometimes you have to click twice at the beginning. It'll advance 1 frame, right? Find the center of it, click, advance 1 frame, and so on. So you're collecting all that data, right? The position of the ball at each frame. And I would go until it's down to about here. Make sure it does not hit the floor, okay? So right before it hits the floor. Then when you're ready, you just click on graph. Then remember, you're going to choose the Y position. Then you'll do another graph, the velocity, and an acceleration. And the fits will be the same. It's going to be a quadratic fit for the position versus time. It'll be a linear fit for the velocity versus time. And then you want to use a sigma, right, the average fit for the acceleration versus time. Okay, and then when you're ready to do the jump, go back to video analysis. Oh, let me get rid of these actually. Okay, so now video analysis, open movie. Let's find the jump. Again, I wish there were more time to for you guys to collect your own movies, but unfortunately we can't do that this semester. So where is my, Okay, so again, make sure you digitize that meter stick. first, right? So you define what a meter is. And then you're only going to analyze the motion of me jumping when I'm in the air. So you have to fast forward, like go to next frame until my feet like clearly leave the ground. So maybe I'd say right there. And then you can go to the magnifying glass, right? And what you're tracking is the little blue marker that's on my hip. In theory, we'd really want to track the center of mass of my body, but that's a lot more complicated, right? We'd have to track like different segments of the body and then create a model that represents center of mass. So to give us a pretty good approximation, we're just going to assume that the hip marker represents a center of mass. So then you would click on it, right? And then it advances a frame and keep tracking until just about before I hit. So I'll just fast forward here. I would say until about, oop, that's too far. I'd say right there, right before I hit the ground again. Okay, so maybe to like right there. So you're gonna track the location of that hit marker. Then you're going to do the same thing with the graphs. You're going to create a position versus time, velocity versus time, acceleration versus time, and copy and paste them into your lab handout so you can analyze them. Okay, so the next part of the lab is projectile motion, right? So think of projectile motion as being basically two-dimensional motion of an object in the vicinity of the Earth's surface where the object is just under the influence of gravity. We're going to assume that there's no air resistance, okay? So actually, let me jump on the iPad to describe like the basics of projectile motion. Okay, so for a projectile, the object is going to be launched at some particular height. Let's say it's launched at this height right here. And there's some velocity it's launched at, right? So it has a magnitude and it has a direction. So I'll call this angle theta the direction. This is like my launch velocity. I'll call it V naught. So what's going to happen? Well, you guys kind of know, right? It's going to rise to a peak, right? The projectile, and then fall back down to the ground here. Typically what people do is right away you would find the X and Y components of that initial velocity, of that launch velocity. So if we project this onto the X-axis, this would be my X component of that initial velocity, so I'll call it V naught X. And then if I project it onto the Y-axis, let me draw a vertical here. So project it onto the Y-axis, this would be the Y component, V naught Y. Now, if we assume that there's no air resistance, right, and we're just talking about the X direction, are there any other forces acting on the ball in the X direction? No, right? If there's no air resistance, there's going to be no other forces acting on the ball in the X direction. So if there's no forces acting on the ball in the X direction, that means the acceleration in the X direction is 0. If the acceleration is 0, what does that entail about the velocity in the X direction? Well, it's constant, right? If the acceleration is 0, the velocity is constant. And in particular, we're talking just about the X direction. So whatever I had for the initial velocity, right, this initial velocity here, it's going to remain the same throughout the motion. So I'm going to draw at the same length, even at the peak here. So something like that. Now, what about the Y direction? Are there any forces acting on the ball in the Y direction? Again, we're going to ignore air resistance. Yeah, we have the gravitational force, right? The weight of the ball. So in the Y direction, it's going to look like free rise, free fall motion. So initially, I have a large positive velocity. That's my V naught Y. Then a little time later, it's going to be positive but smaller, right? And then positive but smaller. At the peak, there will be no velocity in the y. And then after the peak, it'll be negative, first small, then larger, and so on. So something like that. So you can think of projectile motion as consisting of two motions, right? It's constant velocity motion in the x direction and free rise, free fall motion in the y direction. If you put those two together, you get the motion of a projectile. All right, now the thing that's going to be really of interest to us is a special horizontal displacement, okay? So if you look here, like this is the launch height, right? That's where it's launched at. This is like where it hits the ground. So this distance from here to here, that is a horizontal displacement, but there's a very special horizontal displacement, and it's defined to be from the point of projection to a point on the path that's at the same elevation as the point of projection. And this special horizontal displacement, we call this the range. Okay, so a big part of this lab is to look at how varying this launch angle, so if we change this launch angle, how does that affect the range of the projectile? That's like the key thing that we're going to look at in this particular lab. Now, there's a formula for range, and it turns out it depends on several things, right? It depends on, as you might imagine, the launch velocity, like how fast you launch the ball at. In fact, it's v naught squared. It depends on that launch angle, theta, in a complicated way. It's sine of 2 theta. And it also depends on how strong the acceleration due to gravity is. So divide by g, right? So it depends on the launch velocity, the angle theta, and then the value for g. So if we vary any of those things, it's going to change the range, right? If I increase the launch velocity, so if I increase v naught here, and I hold theta constant and g constant, the range has got to increase, right? Because I'm making the numerator larger. If you decrease g, well, how do you decrease g? Well, you obviously can't do that on Earth, but let's say you bring this whole apparatus, the whole launch mechanism, right, the gun, to the moon, where g is like 1/5 of that as on the Earth, and you'll find that the range will increase, right? If I decrease g, I'm going to increase the range, okay? And then the other thing is, if I keep v naught constant and I keep g constant, and that's basically what we did in lab, because v naught is determined by how strong the spring is in the gun, and g is a constant 980 centimeters per second squared, right? It doesn't change. And I vary theta, we want to see what happens to range. So somehow range is going to vary as I vary the angle theta. Okay, let's go back to the handout. Okay, so the first part of this experiment, we need to figure out what that launch velocity is. So what you guys should do is you want to make sure you watch the video. I collected like a short video just describing how I collected all the data for the range and for this to figure out the launch velocity. So basically in this table, I launched the ball at 3 different angles, at 15 degrees, at 45 degrees, and at 75 degrees. And I measured the time it took the ball, meaning the diameter of the ball, to pass through a photo gate that was right on the end of the launcher. And the times are pretty similar, right? Because they're not going to change too much. So in this case, it was 0.0052 seconds, 0.0054, and then 0.0055 seconds. The diameter of the ball is obviously the same, and we're going to use 1.90 centimeters as a diameter. So the first thing that you guys have to do, and this is question 11 here, is you want to calculate the launch velocity for each of these 3 angles. So how do you do that? Well, the velocity is going to be the diameter divided by the time it took the ball to pass through the photo gate, right? So it's 1.90 divided by 0.0052. That'll be your launch velocity for the 15 degrees. Then do the same thing for 45, same thing for 75. Now these are going to be similar. So what we're going to do is we're going to average these three values, and that is going to be your V naught. That'll be the launch velocity that we're going to use for the particular marble gun that you have. Okay, and make sure you show me these calculations in your lab report. Okay, then the main part of the experiment, and again, watch my video to see like how I collected this data. I basically varied the angle, right? 0 degrees, 15, 25, 35, and so on up to 90 degrees. And I measured the range, how far from the edge of the gun to where the ball hit. And basically there's a landing platform with carbon paper, right, and a piece of white paper underneath, so it leaves a mark. And I measured from that mark to the edge of the gun. And these are the values I got. By the way, at 0 degrees, the range is 0. That's given already. And at 90, the range is 0. But in between, I had to measure all those distances. Okay, so I did 3 trials. So for question 12, all I want you to do is to average these values. So you're going to have like an average range for each of those angles. Okay, so just average the 3 trials for each angle. And maybe show me 1 or 2 sample calculations, right, for that average. Okay, then you're going to plot range versus angle, right, using Pasco Capstone. And what you want to do is you want to locate the maximum range and the angle at which it occurred at. But to do that, you have to perform a sine wave fit to your data first, okay? Let me actually jump on Pasco Capstone to show you how to do this part. Okay, so we're in Pasco Capstone. Remember, for graphing, you go to Classic Templates, and then this left upper icon here. So the X is going to be the angle. So this will be angle. And the units are degrees. You can either write out degrees, or if you have a keyboard, if you hold down the Alt key, and on a numpad, you do 2, 4, 8, and lift up the Alt key, you'll get a degree symbol. But you could just write in degrees, that would be fine too. And then the Y is going to be the range. So user enter data, I'll put in range, and that's going to be in centimeters, okay? So let me make up some data to show you like what this should look like. So the angles, well, these will be the same, 0, 15, 25, 35, 45, 55, 65, 75, 90. And then let's say these are my range values, 0, 20, 33, 38, 42, 39, 31, 22, and then 0. Okay, so on the X, I want to plot angle. On the Y, I want to plot range. Actually, that looks pretty good. For the title, I'll put range versus angle. Right, always Y versus X. Okay, get rid of the line connections. And then for a fit, it actually should be a sine wave, right? So we're going to choose like the sine function here, which is this one, the first one, sine function. Hopefully that does a good fit. Actually, that's pretty good. Now, what we want to do, what the question is asking for, is what is the maximum range, right, experimentally, so based on our experimental data, and then what is the angle that it occurred at? So to answer that question, after we do this fit, the sine fit, we want to find the peak of our curve. Not the data point, don't use that data point, whatever your data point is over here. Find the peak of the curve here. So how do you do that? We're going to use the coordinate tool. So if you click on, it's right next to the fit icon to the right of it. This is add coordinate tool. And then we need to change one setting on here. So we need to click on it and then right click. Oh, no, there you go. Click on it, right click, go to tool properties. And then where it says coordinates, this snap to pixel distance, we're going to change that to 1. That just means we have more control over moving the location of this, like the There we go. It's like the crosshairs, right? So if I didn't change that snap to pixel distance, it wants to jump to one of my data points, but I want to have more fine control over it. So I can go right to the peak of my graph, which is maybe right there. Okay, I'm going to rescale that too. Great, that's it. So what it's saying is that the maximum range is this value, right? But that's just the y coordinate here. That's the 41.26 and from the coordinate tool. And that will print out when you print out your graph. And then the angle at which it occurred at, it's right here, 44.81 degrees, right? So you'll have both those values. So now you would do the normal, right? You would copy display and then paste this into your lab report, right? Knowing that you want to record those values. Okay, so let me go back to the handout. Okay, so again, this question is asking, question 13 is asking you to do that plot, right? So you have that, you want to copy and paste it into your lab report. And then it says, compare the theoretical optimal angle. Well, we know that in theory, if we ignore air resistance, 45 degrees should give us the maximum range, okay? So I've already put that in here, 45 degrees. The optimal angle experimental, this is going to be the value from your graph. When you locate the peak of the curve with that coordinate tool, you want to record the angle value, right? It was like 44 point something. I forgot what it was, but you're going to record the value there. And then you're going to compare those two by computing a % experimental error, right? Remember how to do that? You find the difference in its absolute value, so you make it positive, divide by the theory, the accepted, which is 45, and then times 100. Okay, we also, remember when you did that coordinate tool, you also got the experimental maximum range. You can put that value in here into this table, so whatever that range was experimentally in centimeters. And then the other way that we can get the maximum range is theoretically. How do we do that? We can compute it using this equation. R equals V naught squared times sine of 2 theta over G. But remember, theta is 45 degrees, right? Because the optimal angle theory is 45. And when you do sine of 2 times 45, sine of 90, that's just equal to 1. So this formula simplifies to range, the maximum range theory equals V naught squared over G. Well, V naught is your launch velocity. Whatever you guys got for your average up here, you're going to plug in that value, right? Square it. And then G is 980. So you would divide by 980. And that would be your maximum range theory. And then I want you to compare those two values by computing a % experimental error. Okay? So that's for the actual data that I collected, right? The experimental data. The next part, I want you guys to collect some data using the simulation. Okay, so you want to go to the projectile motion simulation. So the link is here. And then what you're going to do is you're going to set this up so that the initial speed of the projectile is 18 meters per second. Now we're going to use SI units for this part of the lab. Use the cannonball as your object that you're going to fire. And fire at angles of 25, 30, 35, 40, 45, 50, 55, 60, and 65 degrees. And use the tape measure to measure the range for each of those angles, and you're going to fill in this table. So again, you have the angle, right? So you want to use these particular angles, and you want to figure out the range in meters. So let me show you what this is going to look like using that simulation. I'll show you how to use the actual simulation. Okay, so here is the website for the simulation. It's that same group from University of Colorado Boulder. They have some really, really cool simulations here. So we're going to click on projectile motion. We're just going to use the intro part. And the first thing you want to do is you want to, let's decrease this launch height so that it's at 0. So we can bring it down to 0. And so it's launching from the ground. And then the launch object over here into the pumpkin, we're going to use cannonball. You want to set the initial speed to be 18, right? 18 meters per second. And then to launch an object, all you have to do is hit the red button here. So it'll launch it. Okay, so how do we get the range information now, the range in meters? Well, here's where you use this little tape measure icon. So I bring it so that the beginning of it is at the cannon. So like right there. And then you can drag the tape measure out to where it hits, let's say right there. And that value, 25.39 meters, that would be the range for 25 degrees, right? When you're launching at 18 meters per second. Then you would increase this to 30 degrees, right? Launch it. And then measure the range, record that, and so on and so forth, okay? Until you get all the values. Okay, so let's assume you have all the values, right? This table's filled out. You're going to do another plot using Pascal Capstone. It's really the same as what you did earlier. You're going to plot angle on the X, just like before, and then range on the Y, but now the range is in meters, right? And do the same thing that you did previously. You're going to do a sine wave fit. You're going to use the coordinate tool to find the peak of your graph, just like we did before. And then the two questions are basically the same. You want to find your optimal angle experimental, and then compare that to, theoretically, the optimal angle should be 45 degrees. So compare it by computing a percent experimental error. And then you want to record your maximum range experimental. Right? Actually, this should be meters here. It's a maximum range experimental. And then the maximum range theory, you can compute. Right? Again, it's going to be V naught squared. Well, V naught now is 18, and G is now 9.8, right? Because we're in SI units. There is a mistake here, though. These should really be meters, right? So the range should be in meters. And then finally, compare those two maximum ranges by computing a percent experimental error. So it's just like you did previously with the experimental data. Now you're going to do the same thing for the simulation data. All right, and then there's one last question. It says, using the simulation, set the bullseye target to be 20 meters from the base of the cannon. Keep the height of the cannon at 0 meters. And then with the angle at 25 degrees, what speed should the cannonball be fired at to hit the center of the bullseye? And then now change the angle to 45 degrees and determine the correct speed to hit the bullseye. And you're just going to fill in your values here. So you're kind of playing with the simulation and figuring out what the speeds, the initial launch velocity must be so you hit the bullseye, okay? Let me just show you that real quick. Okay, so you're going to move, again, the target, so it's at 20 meters away. So right there, 20.0 meters. Set the angle, make sure it's at 0, right? The height is at 0. Set the angle to be 25 degrees. And you kind of have to play with the initial speed and launch it and see what speed is the correct speed so it hits directly in the center of the platform. So let's say you guess it was 20 meters a second. Nope, that's way too fast. So then let's say you thought it was 9 meters a second. Nope, that's way too slow. And then if you play with this, eventually you'll find the correct speed so it hits right in the center of the target. Then you're going to change the angle to 45 degrees and do the same thing. Play around with the speed here until it hits directly in the center of the target. Okay, you're going to find the correct speed. And then that's it. Again, fill in this last table, right? And then make sure you include that table in your lab report. So then it'll be the usual, right? Have one person from your lab group upload the lab report as a PDF in Brightspace, and then I'll grade it and get it back to you. All right, great. Thanks, everyone.